All right, let's just have a look at solving quadratics, because of course now every quadratic can be solved, because we can use imaginary numbers to do it. So x squared plus 3x plus 7 equals 0. We can go to our quadratic formula. In the past, the negative under the square root sign was a problem, but we can now simplify that surd, because we know the square root of negative 1 is I. And so just like other surds where we said, oh well, square root of 20, we could rewrite it as square root of 4 times the square root of 5, and we know the square root of 4. We can now do that with this one, because we can say, well, square root of negative 19, I can write as the square root of negative 1 times the square root of 19. And I know the square root of negative 1, because that's I. And so it becomes negative 3 plus or minus root 19I all over 2. And, well, splitting up into two solutions if we need to. Of course, another way we can do that is now every quadratic can be solved by completing the square, because we can always now write it as the difference of two squares. Because if, like this one, we end up with the sum of two squares, we can turn it into the difference of two squares by changing positive 19 on 4 to be negative 19 on 4i squared. And so everyone can be written as the difference of two squares. So it then becomes x plus 3 on 2 plus the square root of 19 on 2i, x plus 3 on 2 minus the square root of 19 on 2i. So it gives us an alternative way, I guess, of factorising, or not factorising, sorry, solving quadratic equations. We could always just do completing the square for those. And, oh, well, again, there's the two solutions. So what about if we want to create quadratics? We did see this idea back in the quadratics. But now we know all quadratics, if it has real coefficients, and that's the key, then the solutions will always end up in conjugate pairs. Has to, because of the quadratic formula going plus or minus the square root. And that's where the I is going to occur, in the plus or minus the square root. So solutions will always appear in conjugate pairs. But again, I stress, that's if the coefficients are real. If the coefficients aren't real, well then they won't appear as conjugate pairs. So what we're basically saying then is, I know it can always factorise to be x minus some complex number, x minus the conjugate of the complex number. And expanding that out, we get x squared minus z plus z conjugate x, and z times z conjugate for the constant at the end. Well, z plus z conjugate, if you think about it, it's going to be x plus iy plus x minus iy. The imaginary parts are going to cancel. So the middle bit will always be twice the real part of z. And our one at the end, z conjugate, remember we saw that was sum of two squares, which turned out to be the real part squared plus the imaginary part squared. So now, if I've got a quadratic equation with roots 4 plus I, 4 minus I, yes, I could write it as x minus 4 plus I, x minus 4 minus I, expand the whole thing out. But if I think back to what my answer has to be, I can simply go, well, hang on, the sum of the roots will be twice the real part. Twice the real part is 8. The product of the roots would be the sum of two squares. Well, 4 squared plus 1 squared is going to be 17. So I know the equation then is x squared minus 8x plus 17 equals 0. So I don't have to muck around with expanding out the parentheses and all that to get the answer. How do we find the square root of a complex number? So a plus ib is going to be our answer. We want to find the square root of x plus iy. There are actually different ways of doing this. So let's have a look at this one first of all. Well, the first thing I'm going to do is square both sides. So I have a plus ib all squared, because then I can expand out the left-hand side and then use our idea, the real part equals the real part, the imaginary part equals the imaginary part. So if the square root of x plus iy, we've got to find that. The answer is going to be a plus ib. We can set up a set of simultaneous equations. A squared minus b squared will always be the real part. 2ab will always be the imaginary part. So if I want to find the square root of negative 12 plus 16i, a squared minus b squared, negative 12. 2ab, 16. So I'll rewrite the second one to be b is a on 8 on a. Sub that into the first one, and we'll always end up with a quartic. but it's a quartic that can be solved like a quadratic. And so we say what multiplies together to give negative 64, adds together to give 12, and we get negative 4 and 16. So either x squared equals 4, sorry, a squared equals 4, I should say, or a squared is negative 16. Well, a will be plus or minus 2, and the corresponding results for b then would be 8 divided by 2, so plus or minus 4. I probably shouldn't write it like that because that actually implies 4 possibilities. But what I'm trying to get across there is when a is plus 2, b is plus 4. When a is minus 2, b is minus 4. As for the other one, it's not an issue because a and b are real numbers. Right? You might be looking and thinking, well, hang on, no, surely b is imaginary. No, b is the imaginary part, but it is a real number. And a is a real number. And a squared equals negative 16 will not produce a real number. So there's no real solutions to that part. So the square root is plus or minus 2 plus 4i. But here's the interesting bit. And this is where people's opinion on this differ. We're saying find the positive square root of negative 12 plus 16i. Yet I've written down the answer is plus or minus 2 plus 4i. Now when we're dealing with real numbers and we've got a number line, I can very clearly see which one is the positive solution, which one's the negative solution. When you're talking about imaginary numbers, is the positive square root 2 plus 4i, or is the positive square root minus 2 minus 4i? And I guess you're thinking, oh, well, logically it's going to be the 2 plus 4i. But imagine this. Imagine if the solution had been plus or minus 2 minus 4i. Would the negative square root be 2 minus 4i or minus 2 plus 4i? Like, is it important for the real part to be negative or the imaginary part to be negative? This is the problem. That's why I always give 2 answers. I always say plus or minus because I don't believe you can actually determine. Some books will define the positive square root and some questions will define it to be where the real part is positive. Okay, fair enough. If that's how they're defining it, that's how I'll solve it. But if I'm just finding the square root of negative 12 plus 16i, I'll say plus or minus 2 plus 4i because I don't know which one's positive, and you can't order complex numbers. So how do I know what side of 0, if you like, it's on? Is it on the positive side? Is it on the negative side? You can't determine it. Okay, so a plus ib is the square root of x plus iy. Here's another way of solving the same question. We just saw a squared minus b squared is x, and 2ab is equal to y. Now we can use that even further. If I play around with this idea, x squared plus y squared, remember z times z conjugate, that idea of z times z conjugate. And I played around with this a squared minus b squared over here, you see. So I can say x squared plus y squared will be a squared minus b squared squared plus 2ab all squared, so 4a squared b squared. And I can rewrite that and get a to the power of 4 plus 2a squared b squared plus b to the power of 4. So, using that idea, if the square root of x plus iy is a plus ib, then we know a squared minus b squared is always the real part. That bit stays the same. But the other bit is a squared plus b squared is the square root of that idea number times its conjugate, x squared plus y squared. Now, how do I determine the signs? If y is greater than 0, I'm finding the square root of something where y is greater than 0, then a and b will always have the same sign. And if y is the imaginary part is negative, a and b will always have different signs. That's the way it works out with square roots of complex numbers. So if I go back to this question, is it a quicker way of doing it? Well, let's have a look. Got to find the square root of minus 12 plus 16i. So I'm going to say, well, a squared minus b squared is negative 12. Because a squared minus b squared was the real part. A squared plus b squared is the square root of x squared plus y squared. Well, 12 squared is 144, 16 squared is 156, something like that. Well, I said something like that. 256, there you go. But anyway, but add them together, you get 400. Square root of 400 is 20. And now there's the simultaneous, and I think that's a lot easier simultaneous equation to solve than this one up here. Add them together, 2a squared is 8, so a is 2. and therefore b is 4 because the imaginary part was positive. So I know b is going to be of the same sign. So I know a is 2, b is 4, so the square root of minus 12 plus 16i is plus or minus 2 plus 4i, yeah. Okay, let's find the square root of 5 minus 4i. Using this idea, I suppose this is the downside of this method, is you can get messy ones, because a squared plus b squared in this one would be the square root of 5 squared plus 4 squared, which is 41. And we don't know root 41 exactly. So a, when we do it and play around with the numbers, eventually we get a is a half root 10 plus 2 root 41. A little bit messy. And therefore b, when you sub it in to b squared, you get b as a half square root of negative 10 plus 2 root 41. And so the square root of 5 minus 4i is this lovely expression here. It is correct, but it's not very neat. Using the other method, you'd come up with probably a lot neater answer than this one. But that's not wrong. I mean, that is the square root of 5 minus 4i. So I guess this method's great when x squared plus y squared turns into a perfect square. Otherwise, the answer can get a bit messy. Okay, let's solve this quadratic equation. Now, this time you'll notice the coefficients are not real. So the solutions will not be in conjugate pairs. You can still use the same idea. You can say what multiplies together to give 2 minus 2i, what adds together to give 2 plus I, what adds together to give 2 plus I? 2 and I seems logical. Mind you, they don't multiply together to give 2 minus 2i, so bad luck, that didn't work. So generally we'll just go to our quadratic formula. Square root of minus 5 plus 12i, but that's all right. That one will work because 5, 12, 13 is a Pythagorean triad, isn't it? That's basically what you're looking for, the Pythagorean triad, and you know it'll work out nicely. If you remember those from year 7 days, I think it was, or it might have been year 8, whatever it was. So yeah, a squared minus b squared is negative 5, a squared plus b squared is 13. So a turns out to be 2, b turns out to be 3. So I can now sub that in. I've got minus 2 plus I, plus or minus 2 plus 3i on 2. And there's our two solutions. In fact, it was I and minus 2 minus I. No, remember that's minus the sum of the roots. Yeah. Okay, there we go.